Hi, I'm Natasha Morrison and welcome to one of the virtual Cambridge Maths Open Day talks. So today I'm going to tell you a little bit about some of my research. So I'm a research fellow here at Sydney Sussex College, and I suppose if this was a normal open day, you'd have had a chance to have a walk around Cambridge to see some of the colleges, to see the maths department, because obviously you're not able to do that and we're all at home. I thought I'd bring Cambridge to you very briefly. This is a photo of the gardens in Sydney, Sussex a couple of weeks ago. So they're really, really pretty at the moment. And hopefully at some point in the future, you'll be able to visit them in person. But I guess I'm supposed to be talking to you about my research. So imagine a social network. So for example, the people who live in Cambridge. So each person, so this is me, the smiley face at Sydney, Sussex, and each person in Cambridge has some set of people who they know. So you can represent these people on your map of Cambridge, and you can connect them if they know each other. So this is just one example of a network. And very broadly speaking, my research studies structures such as this, processes on these structures, and properties of these networks. So why would we be interested in this sort of thing? Well, in the world, networks are everywhere. So probably almost anything you can think of, is some sort of network. So for example, there are many kind of online networks, such as Facebook is a social network. The London Underground stations form a network. Many forms of our infrastructure, such as the water pipeline or electricity network, right? All of these things in the world are networks, and often when people want to build these things or understand these things, it's helpful to be able to say things mathematically about how they work. So my area of maths is called graph theory, and very roughly speaking, it's the study of networks and their properties. So what sort of questions might people be interested in? Well, I guess a very, very topical question at the moment is, can we predict the way that disease will spread through a social network? So this question is actually vaguely related to what I'm going to talk about today. Before I go into that, let's just have a little think about the other sorts of things that graph theory could be applied to. So for example, suppose you were a water company and you needed to connect certain towns to a water network. Well, you might want to say, well, what's the best way to do this? What's the most efficient way to do this so that I only use a small amount of my water pipes, but I still manage to connect all these towns to the network? You can also ask things about road networks. So what's the best way to design a system of roads that minimizes the way that the amount of time that people have to spend sitting in traffic? Something that I think is really interesting that some colleagues of mine in France have thought about is, can you design or give an efficient system to help people find kidney donors? So just to explain, why should this be anything to do with networks? So suppose I needed a kidney and I had a friend who had the same blood type as me, then perhaps my friend could donate a kidney and I could get it and I'd be happy. But suppose now my friend did not have the same type of blood type as me, but there was another person who needed a kidney whose friend did. Then if my friend had the same blood type as this person who needed a kidney, these two people could, right, my friend could donate a kidney to this other person, and their friend could donate a kidney to me. And sort of as a foursome, we'd all be happy. So we'd be a kind of group, and you could say, okay, grouping these people together means that more people get kidneys and more people are happy. So you can imagine representing this problem as a kind of network where you've got people who need kidneys, people who are willing to donate kidneys for their friends, and you need to kind of find a good system to make small groups of people together in ways that, you know, will facilitate kidney donation. Obviously, I've really simplified this problem, and in the real world there are many more constraints and issues with this than what I've just said, but that's just one example of a problem that can be represented using, you know, networks and our understanding of them. Another fun problem, maybe you've come across before, asks, well, what is the fewest number of colors you need to paint a map in such a way that adjacent regions will get different colors? Now, maybe this is something you've seen. If not, well, the answer is 4. And I suggest you go and look up the 4-color theorem. It's a very nice theorem which says, in fact, any map you draw, you can color it in 4 colors so that adjacent regions will never get the same color. And that's, I mean, the way that people prove this theorem is they use graph theory. Okay, so let me now formally define for you what I mean by a graph, which is, it's our word for network. So how do we visualize these networks? Well, formally, we define a graph to be a pair VE, where V is a collection of vertices. So it's just the nodes of the network are what we call vertices, and E is a collection of edges. So the edges are the connections in the network, and each edge joins precisely 2 vertices. Now, there are people who study things called hypergraphs, and in a hypergraph, an edge can connect more than 2 vertices. But for everything we're talking about today, we're just going to be thinking about graphs where you can imagine an edge is just connecting 1 pair of vertices. Now, for what we're thinking about today, what's important is which vertices are connected. It doesn't matter how you would draw this network on a page. So as an example of this, the 2 graphs I have on the left-hand side of this slide, they're actually exactly the same graph. You can see this because I've colored these vertices. You can see that the red vertex here is joined to the blue, the green, and the pink, and the red here is joined to the blue, the green, and the pink. And you can check that these are exactly the same network. We've just drawn them in different ways. And again, there are some people who study, you know, the different ways you can draw out networks. You could imagine, for example, if you're doing water pipelines, actually how the network physically is represented is very important. For what we're talking about today, the physical representation isn't important at all. So these 2 are exactly the same network. Okay, so let's start with a fun problem, and we'll see a bit later why this is related to this question about how you would model the spread of disease in a network. So imagine an n by n grid, and in our grid we've got n squared little squares. There'll be a picture in a second, and each square is either infected or it's healthy. And we're going to think about a process on this grid. So at each time step of this process, a healthy square will become infected if it has at least 2 infected neighbors. And just under the rules of this process, once a square is infected, it will remain infected forever. So here's an example of this process. So we've got our n by n grid here, we've got an 8 by 8 grid, and let's suppose that these shaded squares are infected and the unshaded squares are healthy. So just as an example of the way this process would work, so at each time step, what did we say? Well, a healthy square will become infected if it has at least 2 infected neighbors. So for example, in the first time step, this square here, it's got 2 infected neighbors. I should be clear. When I say an infected neighbor, I mean a square that shares a side with my square. So this square here has 4 neighbors, And for it to become infected, I need at least 2 of them to be infected. So after one time step, all of these red squares will become infected because they will have at least 2 infected neighbors. And now in the next time step, right, this process continues and these 2 will become infected. They've both got at least 2 infected neighbors. And so the process can keep running and it will get stuck at some point, and it stops at the point where it's not possible for any more squares to become infected. So that means that either everything is infected or anything that's healthy has at most 1 infected neighbor. So for example, here, it does have an infected neighbor, but there's only 1 of them. Hopefully this problem is clear to you. And now the question you can ask about this process is, what is the minimum number of squares that need to be infected at the start of the process so that when you run this process at the end, everything will have become infected? So if we were in Cambridge right now and we were sitting in a room, I'd say take 2 minutes and have a think about it, and then come back to me and we'll discuss what the answer could be. So perhaps for now, what you should do is pause your video, say, think about this for 5 minutes, and then come back and we'll discuss it. So hopefully now you've paused your video and we can talk, have a little talk about what the answer to this question might be. So it's fairly easy to come up with, kind of simple lower and upper bounds for this problem. So trivially, if we only infect 1 square, right, then it's not going to spread at all and the whole grid will not become infected. So a lower bound on this number of squares, right, it has to be at least 1. In fact, much more than 1. You could infect a square over here too, and it's not going to work. You can similarly do kind of trivial upper bounds. So we can say, well, if you infect almost everything in this grid, clearly, it's going to spread. So the question says, what is the minimum number of squares that needs to be initially infected? So to prove an upper bound on this, all we need to do is come up with a construction. So if we find some construction on a certain number of squares that spread to infect everything, well, we know that's an upper bound on this minimum number. So for example, here we've got some upper bound, which is n squared minus 3. Now, in fact, when I ask this question, a lot of the time people come up with this example. I say, what's the best you can do? And a lot of people say, let's color it like a chessboard. So half the squares are infected. And in fact, in 1 time step, right, every single other square will become infected. So this does give an upper bound of n squared over 2. But in fact, you can do much better than this. Because in this example, every square here becomes infected in the first time step. Now, that's really not necessary. You can use squares that become infected in the first time step to infect squares later on in the process. So, for example, this construction, which will have 4n minus 4 infected squares, well, this will also work. So in the first time step, what do we have? Well, this kind of inner ring will become infected in the first time step, and then in the next time step, again, 1 more kind of interior ring will be infected, and eventually it'll get everything. And so you sort of playing with this, you realize that you can take more and more squares away, and hopefully some of you came up with some construction on n squares. So here, there are n squares along the diagonal, and this is an example of a set that will spread to hit the entire grid. So in the first step, we get the diagonals next to the main diagonal, and this, keeps spreading and eventually will hit everything. So this construction gives an upper bound of n on this minimum number of squares. Now, hopefully, when some of you thought about this, you came up with n. This isn't the only construction that will work. there are many constructions of n squares that will work as well. So we've now got an upper bound, which we probably think is quite good. The question is, if we want to determine exactly what this minimum number of squares is, well, we need to come up with a matching lower bound, right? We need to show that no set of n-1 squares can work to eventually infect the whole grid. So what I'm going to do is I will tell you the answer to this question at the end of the talk. But again, it's a really nice problem. So if you want to pause the talk for however long you want, have a think about this question and then come back. I would strongly encourage that you do that. Just a hint before you go. So I can probably express, the solution, why you can get a matching lower bound in 9 words. So there's actually a very simple idea which will give you a proof that you can't do better than n. So if you pause the talk and you think you've come up with something really complicated or it's getting really difficult, perhaps you need to think of a different idea, because the solution is something that's really, really beautiful and really simple. So if you would like to pause the talk, pause it now. Okay, so I promise you I'll tell you the answer to this at the end of the talk, but I also said that we were going to talk about processes on networks, and what I've done so far is I've given you a grid. So what does this have to do with networks? Well, you can express this grid problem as a process on a network. So if you look at this graph here, we've got one vertex for each square of the grid, and we join 2 vertices if they're neighbors in our grid. So the question that we asked about the grid actually can be translated to an analogous question on the graph. We can say, well, what is the minimum number of vertices that need to be initially infected, so that when the process ends, eventually every vertex of this graph will be infected. So you can start with some initial set of infected vertices. We apply the rule that a vertex will become infected if it has at least 2 infected neighbors, where a neighbor in a graph is just a vertex you're joined to. And then you can ask the exact same question. So in fact, this process here on my grid graph is a particular example of a large family of processes that people study on graphs, which are called R-neighbor bootstrap processes. So I'm going to now more formally define for you this more general family of processes that you can think about on any type of graph. So let G be a graph, and we'll have some initial set of vertices, which we'll call A. So now what does the R-neighbor bootstrap process do? Well, at each time step, a healthy vertex will become infected if it has at least R infected neighbors. So in our grid example, R was equal to 2. So a healthy grid vertex will become infected if it has at least 2 infected neighbors. And as in our grid example, an infected vertex remains infected forever. And the process ends when it's not possible for any more vertices to become infected. Now, so we've got our graph and we've got our initial set of infected vertices. We then run this process on our graph. Now, if at the end of the process, every single vertex of the graph is infected, we say that this set A percolates. So the grid question can be phrased as saying, well, what is the minimum size of a set that percolates in the grid? So this R-neighbor bootstrap process is a much more general thing than this particular grid problem. So here's an example of how this process runs on some random graph. So let's say, so these are the shaded vertices will be the infected vertices, and the unshaded vertices will be the healthy vertices. So let's say r is equal to 2 in the first time step. A vertex will become infected if it has at least 2 infected neighbors. And you know, the process continues exactly like it did on the grid. So these 3 now have at least 2 infected neighbors, so they'll become infected. And now this has at least 2 infected neighbors, and so on. And eventually, the process will get stuck at this point because both of these vertices only have 1 infected neighbor in the graph, so it won't be able to spread. So in fact, our starting set here did not percolate. So this R-neighbor bootstrap process, it was originally introduced in the 1970s by some physicists who wanted to study magnetism in iron. But since then, it's been used by people in all sorts of disciplines to model all sorts of very interesting real-world processes. So for example, it's been used as a model of the spread of disease. It's been used to model neural networks in the brain. It's been used by sociologists to model the spread of influence in a social network, to model the spread of fake news through Facebook, and all sorts of things. I guess any sort of process, real world process, where you've got something in a network and it spreads if something kind of is surrounded by enough of it, right? You can imagine that this might be a way to model it. Obviously, real world processes are not just as simple as, I don't know, for example, if 3 of my friends have a cold, it doesn't mean that obviously I have a cold, right? So it's not going to be exactly how things work in the real world. But a lot of the time, for a lot of these processes, using an R-neighbor bootstrap process or a variant of it is a good way of modeling the spread of certain things. So this is why mathematicians are very interested in this process, because it has many applications to other disciplines. So one thing in my research that I've studied is I've looked at this process on a very particular type of network. So in fact, the sort of network where I've studied this process on is not very much like a social network at all. I've been studying this on a very structured sort of network, and you can imagine, so this grid network we had earlier, I've been looking at this process on very high dimensional grids and hypercubes. And I mean, don't worry about what this actually is. This is a 3-dimensional hypercube. This is a 5-dimensional hypercube, but you should just think of these as being very high dimensional grids. And the question that I've thought about on these graphs is exactly the question I asked you about the grid. So the question is, what is the minimum number of vertices in a percolating set? So the minimum number of vertices that need to be initially infected so that when the process spreads as much as it's going to spread, eventually the whole network will be infected. And we call this problem the extremal problem, to find the minimum number of vertices. So why are people interested in this extremal problem? Well, it's because people want to understand the random process. So far we've said, okay, we're going to pick some initial set of infected vertices and see what happens. Well, people are very interested in trying to understand, so suppose you've got some network and you start by infecting each vertex with a particular probability. So for each vertex, toss a coin, and so if the coin is heads, the vertex becomes infected. If the coin is tails, the vertex does not become infected. This gives you an initial infected set, which is random, and it's very interesting to try and work out whether the random set is likely to percolate, because if you think about real world situations, a lot of the time, a lot of processes, it's a much better model to be able to say, to sort of say, okay, it's realistic to expect that a certain proportion of the population have got this particular disease or this genetic mutation or something like that, and you can, you know, a certain percentage, let's pick them randomly and let's see what's going to happen if we start this way. And solving the extremal problem is helpful because it helps us to solve the probabilistic question. Now, what you might be wondering is, right, I showed you these hypercube graphs, and I said, and they don't really look anything like social networks. So why would people be interested in multidimensional grids and hypercubes? And that's because, I guess, if you look at, I guess they come from the physics side. So if you're studying materials in physics, or, you know, very structured things, you can express some of these things as high dimensional grids, and that's why mathematicians became interested in these sorts of problems. Okay, so I'm not going to talk in much more detail about my actual research, but I'm going to tell you the answer to this grid question that I asked you earlier. So we determined that we wanted to prove that the minimum number of squares that need to be initially infected is n. How do we do this? Well, I said that you could express the answer in 9 words. So let's see what this is. So my sentence of 9 words is, the perimeter of the infected area does not increase. So what do I mean by this? Well, let's think about one step of this process. So here's a very small example. So we've got 2 infected squares. What's the perimeter of the infected area? Well, it's going to be 8. Now, after one step of the process, starting with these 2 infected squares, we infect this square here. How does the perimeter change? Well, we lose these 2 from the perimeter, and we gain these 2 in the perimeter. So in fact, the perimeter stays at 8. And in particular, it's not increased. Similarly, if you infect a square kind of this way, analogously, it's not going to increase. And you can check that however, you know, whatever infected area you start with, however a square becomes infected, it's impossible for the perimeter of the infected area to get bigger. So here again, it's when this square becomes infected, it's going to stay the same because we lose 2 and we gain 2. If a square is completely surrounded when it becomes infected, in fact, what's going to happen is the perimeter of the infected area is going to decrease. So before we had these 4 sides here contributing to the perimeter, and now once this square becomes infected, the perimeter has gone down. So once you convince yourself that the perimeter of the infected area doesn't increase, well then, how do we complete the proof? Well, at the end of our process, right, the whole square will be infected. So there's a perimeter of 4n. At each step, it hasn't increased. So at the start, the perimeter must be at least 4n. And it's not difficult to check that this means you must have started with at least n squares. So this gives you our matching lower bound. So that's I guess, we've thought about this problem in 2 dimensions. What about if you want to think about more dimensions now? So now imagine an n by n by n cube. You can analogously ask, well, what is the minimum number of initially infected cubes you need to infect your n by n by n cube? And similarly, right, so you could say, okay, so we've got n cubed little cubes here, and we can say, okay, a cube becomes infected if it shares a face with at least 2 other infected cubes. But each cube in the middle, well, there are 6 possible faces for it to share a cube with. So you can say, instead of 2, why don't we insist that a cube becomes infected if it shares a face with at least 3 infected cubes, or 4, right? You can, it's interesting to consider the generalization both to higher dimensions and also to changing the R of the process. So these are the two questions here, right? What happens in higher dimensions, and what happens if you change the value of R? And just one final question. So we determined that the minimum number of squares that needed to be infected to percolate in the grid was n. But what is actually not known is how many different sets of size n there are in this grid that percolates. So we showed that, right, we saw that this, if you just take the diagonal, that's a set that percolates, but there are many different ways to do this. So here I've got two more examples of sets of size n that percolate in the n by n grid. And it's an interesting question to ask, well, how many ways are there of doing this? Okay, so I think I'll end there. So thank you very much for listening. I thought I'd give you one more picture of Sydney before I leave you. But yeah, I hope all your applications go well. I hope you're all safe and well at the moment, and that you enjoyed my talk. I enjoyed giving my talk anyway. Goodbye.